Graphing transformations. So I'm going to split this lesson. I'm just going to do the first couple parts or the first couple pages for today, and then we'll finish the other pages tomorrow. So if you're at home and you're watching this video, then just make sure you pay attention because the practice assignment won't completely be relevant until tomorrow when we finish the whole note packet. So make sure you just pay attention to what you're expected to do. All right, rules for graphing, and this applies to all of the parent functions that we went over the other day. So we went over 4 of them as far as graphing goes, and then 2 of them I already had the graph for you, and you just have to translate the function in the coordinate plane. We're starting with translations, and translations mean left, right, up, or down. First, we'll talk about a vertical shift, and vertical shifts are specifically going up or down. And a vertical shift is identified in the function when you have a k value. All right, if we use a quadratic function, that's actually what's graphed right here. So if we use the parent graph of a quadratic function, we have f of x is equal to x squared. That's your parent function. The k value is going to be +2 or something like that. So a number that's outside of the parent function. If it's a positive number, then it's going to be going up. And if it's a negative number, then it's going to be shifting down. If I gave you a couple of examples for this graph that you already see, this graph here, I could tell you that the parent function, this blue line, is f of x equals x squared. And then I could tell you that this green line is g of x is equal to x squared, there's your parent function, plus 4. And that's telling us that this parent graph shifted up 4 units. And when I say parent graph, this is the parent graph, which is the same as this right here. So parent graph plus 4 means up 4 units. We could do the same thing down here for the second example. Here we're going to shift down. So we could say g of x, as compared to the parent function, is x squared, let's say minus 3. We have our parent function of x squared, and minus 3 tells us we are shifting down 3 units. All right, both of these graphs are the quadratic function. And of course, they're already graphed for you. If I gave you some examples based on the functions that we learned the other day, let's just look at a couple of them. I'll do 2 different examples. If we had a absolute value function that had a vertical shift, we could have something such as the absolute value of x plus 6. And this is telling us to shift up 6 units. Our parent function is the absolute value function. All right, my second example, we'll use the cubic function. We could have f of x is equal to x cubed minus 4. And this is telling us to go down 4 units. In this case, our parent function is the cubic. So that's just a couple of examples of what a vertical shift will look like. A vertical shift follows the same properties for all functions. So you have your parent graph, and then you have a number either added or subtracted at the end of the function. Next, we're going to look at a horizontal shift. So the horizontal shift is when you translate the graph left or right. All right, if you're translating the graph left or right, it means that your function is going to be directly with the variable. And I'll show you some examples in just a second. What I do want to make note of is this one appears to be the opposite of what you think. So if h is greater than 0, the graph is going to shift to the right. If h is less than 0, the graph is going to shift to the left. However, something that's very important to remember is that the parent graph, we have that up here. Standard form is subtraction. So it's always going to appear as if it's the opposite sign. If h is positive, it's going to be x minus negative h. Or sorry, if h appears to be positive, it's going to be x minus negative h, which is actually your negative value. That's just going to appear to look like a positive number. It's going to show up in your equation as x plus h. So it does get a little bit confusing. You just have to remember with left or right, you're looking at the opposite of the sign. If we look at these examples that I already did for you, we have the quadratic function again. Our blue graph is going to be f of x is equal to x squared. And this green line, let me highlight that in green. This green line appears to have shifted to the right. So we took our parent graph and we shifted it to the right. All right, when we write our function shifted to the right, we include it directly with the variable. So it has to stay in parentheses with the variable, always in parentheses with that term. Here we would have x minus 3 in parentheses squared. Now, this is, again, where it gets confusing. You have a subtraction sign, so you're probably thinking, no, that's the wrong sign. It should have been plus 3. But that is not true, because if it was plus 3, that means it would technically be what I did up here, x minus negative 3. So, you have to think of the opposite. This right here is a shift to the right 3 units. In my other example, we shift to the left. So we have our blue graph, which is our parent function of x squared. And then the red graph is shifting to the left. If we were to write that, we would write it as f of x is equal to x minus, let's do negative 3, in parentheses squared. So your term is directly with the variable, always in parentheses. Also, if you have 2 negative signs, you rewrite that as a positive. So this shows up as x plus 3 in parentheses squared. But this means that you're shifting to the left 3 units. So please, please, please make sure you pay attention to those signs. They appear like they're the opposite, however, they are not. So the standard form of a left or right shift, otherwise known as a horizontal shift, is going to appear to be opposite. If I give you an example, let's do the absolute value function again. If we have f of x, the parent function is just going to be the absolute value of x. But if we want this to have a left or right shift, we have to add something directly with x. So let's do x plus 7. Like we just talked about, standard form is with subtraction, so this would appear as x plus 7. However, it is x minus -7. Therefore, this example is telling us to shift to the left 7 units. Okay, let's take a look at these two examples. Both of these examples are going to use the same parent function, which is f of x is equal to the absolute value of x. So this is where that flip book or your notes is going to be helpful. You have to know what the parent function of the absolute value of x is. I am not going to give that to you. So it's your responsibility to know that the parent function has key points at -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. And I always graph the parent function with a dashed line, just so my final answer doesn't look super busy with all these lines everywhere in it. So this right here is the parent graph. And the parent graph is f of x is equal to the absolute value of x. Now to graph the transformations, we have +4. And +4 is outside of the absolute value bars, or outside of the parentheses is how I was referring to it before, but in this case we obviously have these bars. So if it's outside, that's going to be an up or down shift. That's this column right here, the vertical shift. If we're looking at a vertical shift and we have +4, that means we are shifting this function up 4 units. So for your final answer, you take every point that you plotted from the parent function and you move it up 4 units. This is your parent function. This is your final answer. This is your final answer. You could erase your parent function if you want to, although I don't expect you to do that, so I always leave mine, that way you can see all my work. I think it's kind of nice to look back and see, all right, this right here is my parent function, and then I shifted it up 4 units. So just make sure whatever you do, I clearly know what your final answer is. I tend to use a highlighter. You could use a different color, whatever you need to do. Make sure I know what you're doing on those functions. For number 2, we have f of x is equal to the absolute value of x plus 3. Let's take a second and compare. Here we have the absolute value of x and then +4. Here we have the absolute value of x plus 3 inside of those bars. Number 1 was shifting up 4 units. This one here is telling us to go left or right. Because it's the absolute value of x plus 3, I need to rewrite this in the standard form with a subtraction sign, which indicates that it's actually -3. That tells us that I am moving to the left 3 units. All right, if I'm moving to the left 3 units, I need to make sure I have my parent function points where I can clearly see that I need to slide all of those points left 3 units. Okay, the On Your Own graphs, the answer key is on my website, but I'm gonna go through these right now. I'm just gonna do them quickly. You can follow along either here or check my note sheet on my website. The last part of the notes that we're going to go over today is going to be reflections. And there's actually multiple reflections in the coordinate plane, but in Algebra 2, we're only focusing on reflections in the x-axis. That means if you look at this graph, we are only reflecting across this line here that I just highlighted in yellow. All right, so reflections are just what they sound like. When you look in the mirror, you see yourself back. So if you were reflecting something across the x-axis, if you're reflecting this line across the x-axis, it is literally going to be the mirror image on the other side of the x-axis. And reflections in the x-axis can be identified when the function is multiplied by a value of -1. So for example, this right here is a square root function. The parent function would be f of x is equal to the square root of x. This was the 5th graph that we had in our parent function notes. It's one of the ones where you do not have to memorize the points, but you are going to have to translate it in the coordinate plane. All right, if we have the parent function of the square root of x, then the transformed function or the reflected function is going to be g of x is equal to negative square root of x. So the whole function is multiplied by a value of -1. And that's what gives it the reflection across the x-axis. If we looked at some examples, let's look at a quadratic function. We could have f of x is equal to, the parent quadratic is x squared, so let's multiply that by -1. And that's going to be negative times x squared, which is going to be a reflection across the x-axis. All right, another example could be a absolute value. Let's do f of x is equal to negative times the absolute value of x plus 3 minus 2. All right, this negative sign is multiplied to the whole function. So once again, this is reflecting across the x-axis. Okay, it appears as if the parent function was multiplied by a value of -1. All right, if we do one more, let's just do the cubic function. If we have the cubic function multiplied by -1, we could have something like negative times x plus 4 in parentheses cubed. And here we have our negative sign, which indicates that it is reflecting across the x-axis. Over here is just a completed example for you. So it's something for your reference if you need help on visualizing a graph. Feel free to look back at that example. It's got all of the steps. Examples of reflecting across the x-axis. The first one we have f of x is equal to negative times x squared. In this case, the parent function is y equals x squared, which has parent function points at negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. Okay, and this negative sign that's being multiplied to the function is going to indicate that you are reflecting across the x-axis. When you're reflecting across the x-axis, you can either multiply the y-coordinate by 1, or you can physically count back to the x-axis and then flip it over. And what I mean by that is this point is right here. We're 1, 2, 3, 4 units from the x-axis. So 1, 2, 3, 4 units in the opposite direction. That's your new point. Here we're 1 unit from the x-axis, 1 unit again. 0, 0, 1, negative 1, 2, negative 4. Here's your reflected graph across the x-axis. Again, you could multiply your y-coordinates by negative 1. For example, this point right here is at negative 2, positive 4. This point right here is at negative 2, negative 4. Your x-coordinate is the same. The y-coordinate is multiplied by negative 1. So either way, you can either multiply the y-coordinate or you can physically count. I tend to count. I think it's a little bit faster. I usually do it right in my head. Count how many units I am from the x-axis, reflect it in the opposite direction. Number 2, we have f of x is equal to negative times x minus 1 in parentheses squared. We have the parent graph of y equals x squared, which is the quadratic function again. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. Okay. X minus 1, that's shifting to the right 1 unit. So let's go ahead and do that. Shift all points to the right 1 unit. This is not our final answer. So far, all we did was shift to the right. Lastly, we need to reflect over the y-axis. Reflect over the x-axis. When you have a graph with multiple steps, you always work from the last step that you were at. You never go back to the original. This one right here that I'm labeling number 1 was our first graph. Then we shifted that graph 1 unit to the right. That's the orange graph. Then we reflect that orange graph across the x-axis to give you this blue line, which is your final answer. Always work from the step before. Do not go back to the original. In the next part of the notes, we're going to talk about dilations. We're going to specifically talk about vertical dilations. That means the graph will appear to stretch or shrink with respect to the y-axis. There are horizontal dilations. We will not be doing them in Algebra 2. All right, so if you have a dilation, that means you're going to have a number multiplied in front of your function. So it's going to appear that you have a leading coefficient. For example, if I gave you f of x is equal to 2 times x squared, this number right here is your dilation number. It is your a value. If a is greater than 1, then the function is expanded vertically. This appears as if you grabbed the y-axis, which is right here, and you pulled on just the y-axis. Pulling on the y-axis is going to take what is your original parent function, and it's going to expand it vertically, which appears to pull it closer to the y-axis. So it looks like it gets taller and narrower. If a is between 0 and 1, then it is compressed vertically. That appears as if you took the parent function and you pushed on the y-axis. So you made the function, what do I want to say? You compressed the function, so you made it appear as if it was wider with respect to the y-axis because you are compressing it. You're pushing down on it, so it's making it get wider. Notice that right here it says if a is between 0 and 1. Recall that if a is less than 1, it's a negative number, and that's a reflection, which we talked about previously on the note sheet. If we look at these two examples, both of these examples have the parent function of x squared. For the first example, this one, if I gave you a potential example of what this could be, it could be something such as y equals 2 times x squared. If I gave you an example of what this graph could potentially be, it could be something such as y equals 1/2 times x squared. In both of these cases, recognize your a value. 2 is greater than 1, so it's a expanding function. 1/2 is less than 1, so it's a compressing function. Looking at some examples, let's look at an absolute value function. If we have an absolute value function and we want to expand it, that means we could have something like 4 times the absolute value of x. So I'm saying that the value of 4 indicates that we are expanding, or in more basic terms, we are stretching the graph vertically by a value of 4. If we looked at a cubic function, we could do a cubic function, let's do 1/3 times x, let's do x minus 2 in parentheses cubed. So not only does this have a multiplier or an a value, which this is a compression, so it looks like it's shrinking vertically or getting compressed vertically. This one also has a shift to the right. So just make sure you pay attention when you have multiple transformations going on. On the right side of your paper, here is a function that is already graphed. This function has 2 additional steps. This graph is shifted to the left 1 unit, and then it is expanded vertically. Right here you can see the parent function, then it moves to the left, then we expand this function vertically, which appears as if you were pulling on the y-axis. So grab the top and the bottom of the y-axis, pull on it, and it's going to make the function stretch out. or it's going to expand it vertically. Graphing dilations. For the first function, here we have f of x is equal to 2 times the absolute value of x. Our parent function is the absolute value of x, and that has key points at -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. This value of 2, this a value right there, is going to tell us that the function is expanding vertically by a value of 2. So if it's expanding vertically by a value of 2, you need to multiply the y-coordinates of the previous graph by 2. We could make a table and we can multiply the y values by 2, or you can do it right in the coordinate plane. I tend to do it right in the coordinate plane. I think it ends up being a little bit faster, but you could make a table off to the side. I'm going to show you both of them right now, and you can do it however you want to. So starting at this point, that point is located at -2, 2. And I'm writing it out for explaining purposes, but if I was doing this on the graph, I would just do this in my head. The y-coordinate is 2. We're going to have to multiply the y-coordinate by 2 in order to graph that dilation. So multiplying this y-coordinate by 2 would be 2 times 2, which is at 4. So our new graph is going to have a point at 4. This point right here is at -1, 1. We have to multiply that y value by 2. 1 times 2 is 2. Notice that I am not changing the x value. The x value is remaining the same. So both my original point and my new point are on these purple highlighted lines that I just graphed. So the x coordinate is not changing. It is just the y coordinate. Here we have a point at 0, 0. Take a look at that y value. 0 times 2 is still 0, so this remains at 0, 0. 1, 1. 1 times 2 is 2. And 2, 2. 2 times 2 is 4. Okay, that's your final graph function. Again, when you are performing a dilation, whether it's a stretch or a compression, you are multiplying the y values by your a term, or the multiplier in front of your parent function. If you were to make a table of values for this, you would make a table of values from the previous graph. In this case, our previous graph was just our parent function. So we have values at -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. You would make another column on your table, and you would multiply the y coordinates by 2. 2 times 2 is 4. 1 times 2 is 2. 0 times 2 is 0. 1 times 2 is 2, and 2 times 2 is 4. Then you would graph your new ordered pair, so your new x value with your new y value. That point is at -2, 4. That's the point we graphed right here. Next we have -2, 1. That is this point right here. Next 0, 0, then 1, 2, and 2, 4. So based on our table of values, we're going to end up with the same answer that we graphed in pink. Completely up to you whether you want to perform those operations right on the graph or if you want to make this table off to the side. It's up to you. Number 2 is the same parent function. The parent function is the absolute value of x. We have ordered pairs -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. Here's our parent graph. You have to recognize that you have an a value of 1/2. That indicates that you need to multiply the y coordinates by 1/2 or divide by 2. Same thing, multiply 1/2 by 1/2 or divide by 2. All right, here we have a point at -2, 2. If we look at our y value, 2 times 1/2 or 2 divided by 2 is 1. This point, same x value, graphed at 1. Here we have a point at -1, 1. 1 times 1/2 or 1 divided by 2 is 1/2. 0, 0, 1, 1/2, 2, 1. And this is your final answer. If we look at the two graphs that we have here, we have number 1, which is 2 times the absolute value of x. That's a stretch. You can see this graph looks like it was stretched out, pulled up, so pulled on the y-axis. Number 2, we have 1/2 times the absolute value of x. And this graph looks like you touched the top and the bottom of the y-axis and you pushed on it, meaning it's compressing the graph. It's making it closer to the x-axis. Now that we've gone through all 4 transformations, we need to understand that there are steps for a sequence of transformations. That means that you need to follow a certain order when you have multiple transformations happening in the same function. So the first step that you're going to do, no matter what the function is going to be your horizontal shift. That means if you're shifting left or right, you need to do that first. The second step is to perform any multiplication, so dilations. This means if you are stretching vertically or compressing vertically. The third step that you would perform is reflections. And we are only looking at reflections across the x-axis. And the last operation that you do is the vertical shift. And the vertical shift is when you shift up or down. Make sure you follow this order because you might end up with a different answer if you follow or you do these in a mixed up order, especially if you have a reflection and a vertical shift. These two are the ones that are super important to follow the correct order in. So just to quickly repeat, we have a horizontal shift which will happen first, then our dilations, then any reflections, and then a vertical shift, which is up or down. All right, if we look at the two graphs here, These are graphs where we're combining multiple procedures. That means we need to follow this order right here. For number 1, our parent function is going to be y equals x squared, which has key points at -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. The first step that we need to perform is our left or right shift. In this case, we are shifting this graph to the right 2 units. And that's our first step. Based on the order above, the first thing we do is our left or right shift. We take all our points, we shift them right 2 units. The next thing we look at is dilations. We have a dilation of 3. This would be a stretch. So a vertical stretch by a value of 3. And that's the second step. If you have a vertical stretch, that means that you are multiplying all the y coordinates of your previous function by 3. The previous function is the last function that you graphed, which is the function in blue. It is this function right here. So we need to multiply all the y coordinates by 3. And I'm going to do this right in the graph. This point right here has a y coordinate of 4. 4 times 3 is 12. This does go off the coordinate plane a little bit. That's okay. We can just make a mark above the y-axis. This point has a y coordinate of 1. 1 times 3 is 3. Here we have a y coordinate of 0, which will remain in the same location. This point has a y coordinate of 1 times 3 is 3. And right here we have a y coordinate of 4 times 3 is 12. Your x values do not change. Make sure those remain in the same location. All right, so the green graph is my second step, which was my vertical stretch. So vertical stretch by a factor of 3. And my last step is right here, which is my vertical shift, which is my vertical shift. I am shifting up 1 unit. I take every point on that green graph, the second step there, and I shift it up 1 unit. I'm going to forget about those top 2 points just because they fall off the graph on my paper. So I'm going to come down here and I'm just going to plot every point up 1 unit. My final graph will only have these 3 points on it, but I can still see that I have the U shape. So I am all set. That's good enough for my final answer. Number 2, we have f of x is equal to negative x cubed plus 2. The parent function is x cubed and has points at -2, 8, -1, 1, 0, 0, 1, 1, 2, 8. Following the directions above, the first step would be left or right shift, which we do not have here. Next, we have dilations. That would be a stretch or a shrink with respect to the y-axis. We do not have a dilation or an a value. Next would be our reflections, which we do have. We have a reflection across the x-axis. That means we take every point on this black dashed line and we reflect it across the x-axis. I'm just going to count. This point right here, down here, is 8 units from the x-axis, so I go 8 units above the x-axis. And the last step is your up or down shift. We are shifting up 2 units. That means every point on the blue line gets shifted up 2 units, which gives you the final graph. And that's your answer. For the last section of the notes, we're going to describe how the graphs of f of x and g of x are related, and then we're going to write an equation for g of x. In the description right here, it's telling us that f of x is the quadratic function, or x squared. If I look at the first graph, and I know that f of x, which is our starting point, or we could call it our parent function, is x squared, I know that my parent function looks something like this, and I'm just sketching it quickly. All right, now from there, if I'm comparing this graph highlighted in yellow to this graph here highlighted in purple, I need to look and see what's similar or what's different about them. The first thing I recognize is that the yellow graph, in order to overlap onto the purple graph, would have had to move over 1, 2, 3, 4 units to get to the point of where it's at. So that means we shifted left 4 units. And then I recognize that once it shifted left 4 units, it would be right here somewhere. That graph flipped over the x-axis. So then we reflect it across the x-axis. Okay, if we're writing a function and we're starting with f of x, which is equal to x squared, we just have to work backwards and kind of think about what's going on. So we're starting here. We know that from there we're going to have to shift left 4 units. And then we know that we're going to have to reflect this across the x-axis. Okay, so our new and final function is going to be, and just piece this together, so think about it for a second before you write it down. But combining all of this stuff here, I know that I'm reflecting, so I'm going to have to start with my negative sign. And then I have x minus negative 4, because we're shifting to the left, squared. And when you are subtracting a negative, it's the same thing as adding. So my final function for g of x, or for the graph that I highlighted in purple, is going to be negative x plus 4 in parentheses squared. And number 2, we're going to do the same thing. We have our starting point, which is our parent quadratic function. How do we get from the starting point to this graph right here? Well, this one looks like it's just some shifts left and right. I'm sorry, left, right, up, or down. It appears to me as if we shifted over 1 unit, and then we shift up 2 units. And that's where our new function is. So listing, like we did before, we have f of x is equal to x squared. First, we are going to shift left 1 unit. Then we are going to shift up 2 units. Combining our info, we have g of x is equal to x plus 1. I'm going to skip the step of writing a double negative and just go right to a plus sign. We have x plus 1 squared plus 2.